3 argument forms and substitution instances. In the previous section, the alert reader probably noticed a slight discrepancy between the official argument forms MP and MT, on the one hand, and the actual argument forms appearing in the proofs of the validity of a1, a3. For example, in the proof of a3, I said that R follows from P and PR, in virtue of modus ponens. Yet the argument forms are quite different. MPPQP, QMPPRP. Our MP looks somewhat like MP. If we squinted hard enough, we might say they look the same. But, clearly, MP is not exactly the same as MP. In particular, MP has no occurrences of negation, whereas MP has 4 occurrences. So, in what sense can I say that MP is valid in virtue of MP? The intuitive idea is that the overall form of MP is the same as MP. MP is an argument form with the following overall form. Conditional formula antecedent. Consequent, the fairly imprecise notion of overall form can be made more precise by appealing to the notion of a substitution instance. We have already discussed this notion earlier. The slight complication here is that, rather than substituting a concrete argument for an argument form, we substitute one argument form for another argument form. The following is the official definition. Definition: if A is an argument form of sentential logic, then a substitution instance of A is any argument form A that is obtained from A by substituting formulas for letters in A. There is an affiliated definition for formulas. Definition: if F is a formula of sentential logic, then a substitution instance of F is any formula F obtained from F by substituting formulas for letters in F. Note carefully, it is understood here that if a formula replaces a given letter in one place, then the formula replaces the letter in every place. One cannot substitute different formulas for the same letter. However, one is permitted to replace 2 different letters by the same formula. This gives rise to the notion of uniform substitution instance. Definition: a substitution instance is a uniform substitution instance if and only if distinct letters are replaced by distinct formulas. These definitions are best understood in terms of specific examples. First, MP is a uniform substitution of MP, obtained by substituting P for P, and R for Q. The following are examples of substitution instances of MPPQP and QRPQPRPP and QPQ. QRPR: whereas MP is a substitution instance of MP, the converse is not true. MP is not a substitution instance of MP. There is no way to substitute formulas for letters in MP in such a way that MP is the result. MP has 4 negations, and MP has none. A substitution instance F always has at least as many occurrences of a connective as the original form F. The following are substitution instances of MP. P and QP, QP, QRP and QP. PQQ. Interestingly enough, these are also substitution instances of MP. Indeed, we have the following general theorem. Theorem: if argument form A is a substitution instance of A, and argument form A is a substitution instance of A, then A is a substitution instance of A. With the notion of substitution instance in hand, we are now in a position to solve the original problem. To say that argument form MP is valid in virtue of modus ponens MP is not to say that MP is identical to MP, rather, it is to say that MP is a substitution instance of MP. The remaining question is whether the validity of MP ensures the validity of its substitution instances. This is answered by the following theorem. Theorem: if argument form A is valid, then every substitution instance of A is also valid. The rigorous proof of this theorem is beyond the scope of introductory logic.